an algorithm for so we discuss an algorithm to find GCD of polynomials. And what is the procedure? Find CD. And it is exactly similar to the Euclidean algorithm to find GCD. So we'll see examples so that you can understand. Find GCD of find greatest common divisor find the greatest common divisor of fx is equal to x raised to 6 plus x plus 1 and gx is square plus. Now we want to find GCD, means first step is the first step. First step is find Q and R, quotient and remainder when we divide fx by divide. So how to divide? So by synthetic division or long division, so divide fx by gx and get quotient and remainder. Right, so divide fx by gx and get quotient and remainder. So how to divide? This is the procedure. So fx is x raised to 6 plus x cube plus x plus 1 and x square plus 1. All of you know this division, synthetic division, correct? The question, divide first term, largest degree term of fx, x raised to 6 by largest degree term of gx, which is x square. But we get x raised to 4, right? Then multiply by x raised to 4. So multiply by x raised to 4 to x square plus 1. So x raised to 4 into x square plus 1. What you get? X raised to 6 plus x raised to 4. So x raised to 6 plus x raised to 4 and subtract, change the sign. So this x raised to 6, x raised to 6 gets cancelled, minus x raised to 4 plus x cube plus x plus 1. So remaining terms carry forward. What is the next similar key? Now highest degree term here is minus x raised to 4 and then divide by x square. So minus x raised to 4 divided by x square. What you get? Minus x square. And then minus x square. So minus x square multiplied by x square plus 1. Correct? So what is this product? Minus x raised to 4 minus x square. So the quotient term is here minus x square multiplied minus x square is x square plus 1, but you get minus x raised to 4 minus x square. So change the sign because you want to subtract, and ultimately what we get, so x square minus x raised to 4 minus x raised to 4 is 0. So x cube plus x square plus x plus 1. This is what the expression is. Now same procedure, x cube divided by x square, what we get, x. So this highest degree term and here highest degree term. So x, and then x into x square plus 1. What you get, x cube plus x. So x cube plus x. Now subtract, so change the sign, right? So x cube 0, x square as it is, and x minus x 0, this cancels, plus 1. Right. And so what is the next? X square divided by x square is 1. Here I need to add x and then 1. X and multiply 1 with x square plus 1. What I get? X square plus 1. So x square plus 1 as it is, subtract, so 0. So remainder is 0 in this case. Right. So here x raised to 6 plus x cube plus x plus 1 is equal to, what is the quotient? What is the quotient we get here? X raised to 4 minus x square plus x plus 1. X raised to 4 minus x square plus x plus 1 into x square plus 1 plus remainder is 0 now. Remainder is 0 means what? The x square plus 1, this polynomial is actually factor of this polynomial. Right, that means gx divides fx, and remainder is 0, therefore what is the GCD? Therefore GCD of fx and gx, what is the GCD of these two polynomials?
1 x.
Gx, because the remainder is 0, and then what is the previous dividend or terms which divisor? Gx. So GCD is x square plus 1. Actually f of x is x square plus 1 into x raised to 4 minus x square plus x plus 1. So this is a factor. G of x is a factor. So GCD is gx. Is it clear? Is this clear? Find GCD of fx is equal to x cube minus 2x square plus 6x minus 5, and gx is equal to x square minus 2x plus 1. So find GCD of these two polynomials. Procedure is same. First of all, divide. So x cube minus 2x square plus 6x minus 5. Right? Divide this polynomial by x square minus 2x plus 1. Right? So x cube divided by x square, what you get, quotient x, put here, and then x into x square minus 2x plus 1. So it is x cube minus 2x square plus x. So x cube minus 2x square plus x. So change the sign because you want to subtract. Plus becomes minus and minus. So x cube minus x cube 0, minus 2x square plus 2x square is 0, and 6x minus x is 5x minus 5. Right, what is the next step? What is the remainder here? What is remainder?
X minus 5.
Right, here remainder is because we cannot go further. Right, if we divide 5x by x square, then it is 5 by x, which is not a polynomial. right? So we cannot divide by higher degree term to lower degree term. So remainder is 0 because degree of remainder. So here q1x is x and r1x in first step is 5x minus 5. And would you observe that degree of r1x is less than degree of gx. Here we have to stop, right? We cannot divide further. So this is the first step. What is the next step in division Euclidean algorithm? Fx is equal to q1x into gx plus r1x. We are at this step and r1x is 5x minus 5 which is non-zero. So next step, what is next step? So next step 2,
Okay, sir.
right? So divide gx. What is gx? X square minus 2x plus 1 by r1x. What is r1x? 5x minus 5. Right? So second step now divide gx by r1x because in first step we divide gx, divide fx by gx and remainder is r1. Now so divide okay, divide gx is x square minus 2x plus 1 and 5x minus 5. So what is the first step? Divide x square by 5x, x by 5, x by 5 into 5x minus 5. What is it? X square minus x. You check whatever I am writing, you check the calculations, right? So x square minus x, fine. So quotient is x by 5 here, and what is multiplication? X square minus x. Change the sign. What you get? X square cancels. Minus 2x plus x is minus x plus 1. Right, still degrees are same. Degree of this remainder and 5x minus is same. Still we can divide, right? Minus x divided by 5x. What is it? Minus 1 by 5. And therefore minus 1 by 5 into 5x minus 5. So multiplication is minus x plus 1. Alright. So quotient is minus 1 by 5. Multiplication is minus x plus 1. So change the sign. What you get? 0. Okay, so here remainder is 0. Therefore, gx is equal to 5x minus 5 into quotient. What is quotient? Quotient is x by 5 minus 1 by 5 plus remainder is 0. At this stage, remainder is 0. Right? Here, q2x quotient is x by 5 minus 1 by 5 and remainder is r2 which is 0. And therefore, GCD is of fx.
5x minus 5.
Right. Then what is the previous non-zero remainder? The previous non-zero,
Minus x
right?
plus 1.
For GCD of fx and gx is, so previous remainder is 5x minus 5, right? In previous step remainder was this, and in next step immediately next step remainder is 0. So this is GCD 5x minus 5. Okay, so the algorithm is clear, no doubt in the algorithm. So you,
Excuse me, sir.
yes,
Sir, can you please scroll up?
yes,
Can you please scroll up
which step?
in first question?
This.
First
Previous
question.
this
Yes,
problem.
yes. Yes,
Ah.
sir.
So in this case, remainder is 0, and therefore x square plus 1 itself is a GCD.
Sir, in this case, remainder is minus x.
There is
I'm
minus.
getting minus x.
No, remainder is 0 because x get cancelled in the previous step. Right? X is already eliminated, got eliminated in the previous step. You can see the on screen. Right? Is it clear?
Okay, sir.
Right. Now find GCD of fx is equal to x raised to 4 minus x cube minus 2x plus 2 and dx is equal to x cube plus x minus 2. Now you do this as an exercise because not difficult to find GCD. Find GCD of fx is equal to x cube plus x square plus x plus 1 and gx is equal to x square minus 1. Also find polynomials px and qx such that GCD of fx and gx is equal to fx into px plus gx into qx. We can express GCD as a combination of these two polynomials. So, which we did for integers, same thing it is possible here. Can we express 5x minus 5 as a combination of fx and gx? So, follow the reverse steps. That's exactly similar to integers. Right, find GCD of fx is equal to x raised to 5 minus x raised to 4 plus x cube minus x square plus x minus 1 and gx is equal to x square plus x plus 2. So express GCD as a combination of fx and gx. Right, so express GCD as a combination of fx and gx. Fine. So, okay, is it clear? The method is clear. Algorithm is clear.
Yes, sir.
Right. Okay, now we'll go to the next say topic regarding polynomials. So, uh, theory of equations means we discuss roots of polynomials. So, we in the previous section we discussed about polynomials. Polynomials has a algebra of polynomials, that means addition, multiplication, division. And when we talk about division, then we can talk about GCD, greatest common divisor. And greatest common divisor exists in case of polynomials. And the greatest common divisor is helpful to understand the roots of polynomial. And roots of polynomial is useful to solve many equations which are occurring in solving real life problems. So therefore we need to understand how to solve the polynomials, right? So now we discussed that, recall that so if fx and gx are any two polynomials, then by division algorithm there exists qx and rx such that there exist two polynomials qx and rx such that fx is equal to gx into qx plus rx. So rx is a remainder, right? Where rx is 0 or degree of rx is strictly less than degree of gx, right? So now let us see some example. If f of x is equal to x cube plus 5x plus 5x square plus 3x plus 7, for example, and gx is equal to x minus 2. Now what is the remainder when we divide this polynomial by x minus 2? Let us see what is the remainder. So f of x means x cube plus 5x square plus 3x plus 7 and x minus 2. So what is question now?
Square.
X square x cube minus 2x square, change the sign, then 0. So here 7x square plus 3x plus 7. What is the next question? Next question, 7x. 7x.
7x.
X. This
7x.
one.
What is 7x square minus 14, right? X, correct? You check the sign calculations, what we get at the end. So 7x minus 14 is 0. What is it?
17x plus 7.
So what is next?
70.
17.
So 17x minus minus 34. Change the sign. What do you get? Remainder
41.
is
41.
41. 41. So 41 is remainder. Definitely understand that we are dividing by a polynomial of degree 1, and therefore remainder has to be degree less than 1. That means 0. That means constant. So degree of remainder should be less than 1 because degree of this polynomial by which we are dividing is 1. So degree of remainder should be less than degree of Rx should be less than degree of Gx. But degree of Gx is 1, and therefore what is the choice for degree of Rx? 0. That means constant. So remainder is constant. But moreover, if you evaluate this polynomial at 2, what is f of 2? If I replace, I am just evaluation of polynomial at 2. So evaluate polynomial at 2 means what? If I substitute x is equal to 2, then what happens? 2 cube plus 5 into 2 square plus 3 into 2 plus 7. What is it? 8 plus 4 into 5, 20 plus 6 plus 7. What is it? Is it 41?
Yes.
Yes. Correct. And therefore this gives us some general result, right? So this is called as remainder theorem. What is a remainder theorem, and is this true in general? So if so, let f of x is a polynomial in Rx and alpha is a real number, right? Alpha is some real number, whatever it may be. If f of x is divided by gx, which is x minus alpha, whatever is alpha doesn't matter, then the remainder is what should be remainder by our previous example or discussion? What do we expect? What do we expect? Remainder is evaluate polynomial at alpha. Whatever is the number, that is remainder. The statement is clear. What is the meaning of statement? F of x is a polynomial. You choose any real number, and if you divide that polynomial by x minus alpha, necessarily remainder must be f alpha. Yes, statement is clear.
Yes, sir.
Yes, sir.
Okay, so let us try to prove this result, see why it is true. So let f x belongs to Rx and degree of fx is greater equal 1. It is not a constant polynomial, otherwise we cannot divide. So let alpha is a real number, right? Alpha is, choose any real number. We are considering some polynomial whose degree is greater equal, and now choose any real number of your choice. So let gx is equal to x minus alpha. This is a polynomial of degree. This is a polynomial of degree 1, and degree of fx is some higher degree, whatever greater equal 1. Now by division algorithm, now we want to apply division algorithm to fx and gx, right? By division algorithm, what will happen? What should I say now? There exist two polynomials qx and rx in the set of all polynomials such that fx is equal to gx into qx plus rx, where what is the condition on rx? Rx is a remainder. What is the condition on Rx?
Rx is less than Gx.
Rx is 0
Rx
or
equals to 0.
degree of Rx is less than degree of Gx.
Yes.
But what is Rx is 0? That is Rx is 0 or degree of Rx is less than degree of Gx. But what is degree of Gx? What is degree of Gx?
1.
1.
1, and therefore degree of Rx is less than 1. What is the choice for degree of Rx if it is less than 1?
0.
0.
Rx is 0 polynomial or it is non-zero but degree is 0. That means Rx is a constant. Right, when we divide fx by gx, then necessarily Rx is a constant. That is fine. Or constant c. Let us see it is. Let us say that it is a constant. Therefore, f of x is equal to x minus alpha into qx plus c. What is c? C is constant polynomial now, because we are sure that the remainder is constant. Right. Now evaluate this at alpha. Now evaluate this. That means f of alpha is equal to alpha minus alpha into q of alpha plus c. Right? Because these two sides are equal at x. And now evaluate this polynomial at alpha. X is equal to alpha. So ultimately what we get? Alpha minus alpha is 0. Therefore this term is 0. C. Therefore c is f of alpha. And therefore what is the remainder? Therefore f of x is equal to x minus alpha into qx plus f of alpha. Therefore remainder is f evaluated at alpha. Okay, is it clear? Yes. Is proof clear?
Yes, sir.
8x raised to 2 plus, right? Find the remainder when f of x is divided by x minus x plus 1. Find the remainder when this polynomial is divided by x plus 1. Can you tell me what is the remainder immediately in 5 seconds?
f of minus 1.
F evaluated at minus 1, because this is actually x plus 1 is x minus minus 1. And what is alpha in this case? Alpha is minus 1. F of this minus 1 minus 5 plus 7 plus 3 plus 8 plus 20, 20. Whatever is this number is a remainder. Immediately we can. The theorem which we have proved is in general true. Right? Okay, so now next question I would like to ask. Find, so let f of x is equal to x square plus 2ax plus 7. Find the value of a, so that find the value of, say that x minus 1 is x minus 1 divides f of x. Find the value of a, so that this polynomial x minus 1 divides this. Right? How will you find the value of a, so that this will divide this polynomial? And what is the simple trick? If x minus 1 divide x square plus 2ax plus 7, then the remainder is 0. 0, right? If this polynomial divides this polynomial, then what should be the remainder? 0. Am I right?
Yes, sir.
But if x minus 1 divides x square plus 2x plus 7, the remainder is, what is remainder? By remainder,
f of 1.
f of 1. But what is f of 1? 1 plus 2a plus 7.
2a plus 8.
Right, so 2a plus 8, and we know that when this polynomial divides this, remainder must be 0, right? Therefore which is equal to 0. That means what is the value of a? Minus 8 by 2.
Minus
Right.
4.
Right.
Minus
And
4.
therefore the value of a is minus 4, so that this polynomial will divide this. And here we used remainder theorem. Okay. Okay, now okay, look at this. Suppose you are given polynomial f of x in Rx, and and alpha is a real number. So if we divide f of x, okay, so note this. If we divide f of x by x minus alpha, then the remainder is f of alpha.
F of alpha.
Fine. Now on the top of that, if alpha is a root of f of x, right? What is alpha? Alpha is a, okay, so let us first define the what is the root of a polynomial. So first we'll define what is the root of a polynomial. So let fx belongs to Rx be a non-constant polynomial. Non-constant means what? What is the meaning of non-constant? When I say
Degree of
non-constant,
fx is greater than 1.
Greater than
okay, degree of fx is greater equal 1. If degree is 1, that is also fine, right? But degree should not be 0. A real number, a number or real number, I should not say real number, a number, because root can be a complex number. A number alpha is said to be the root of fx if f of alpha is 0, right? F of alpha is 0. So when we say that number is a root, if it satisfies the polynomial, that is number alpha is a root of fx if it satisfies the equation f of x is equal to 0. If it satisfies this equation, then alpha is a root of polynomial. That is a definition. So now we are talking about this key. If we divide polynomial by x minus alpha, then f of alpha is a root. F of alpha is a remainder. So now if alpha is a root, if alpha is a root of fx, then what happens? F of alpha is
remainder will be 0.
so f of alpha is 0. So therefore, if we divide f of x by x minus alpha, then what happens? If we divide f of x by x minus alpha, then what happens? Then remainder is f of alpha, and alpha is root, therefore 0. Right? So if alpha is root of a polynomial, and if you divide polynomial by x minus alpha, then remainder is 0. This is our next theorem. remainder theorem, factor theorem. Factor theorem means what? If remainder is 0 means what? X minus alpha is a factor. Right? When divide polynomial f of x by x minus alpha, remainder is 0, that means x minus alpha is a factor of polynomial. So what factor theorem states? If so let f of x belongs to Rx with degree of fx is greater equal 1. Let alpha is a real number, then alpha is a root of fx if and only if x minus alpha is a factor of fx. This is if and only if. Alpha is a root if and only if x minus alpha is a factor. So how would you see this? So first assume that alpha is the root fx, right? So let gx is equal to x minus alpha. So by remainder theorem, if we divide f of x by gx, then remainder is
F of alpha.
f of alpha, right? So therefore f of x is equal to some qx into gx plus f alpha, remainder is 0, where qx is some quotient in Rx, right? Quotient. But since alpha is a root of fx, by definition of root, f alpha is 0, right? And therefore fx is equal to qx into gx. That means x minus alpha into qx, and therefore x minus alpha is a factor of fx. Factor means it divides polynomial actually. That is x minus alpha divides fx. Now conversely, what is the converse way? If and only if. So alpha is a root if and only if x minus alpha is a factor. So we assume that alpha is a root, then x minus alpha is a factor. Converse is easy to see because conversely, suppose that x minus alpha is a factor of fx, then there exists another polynomial, some polynomial hx in Rx, such that fx is equal to x minus alpha into hx, right? Because x minus alpha is a factor, so there is another factor. Product is fx, right? And therefore, if we substitute evaluate polynomial at alpha, then alpha minus alpha into h alpha, whatever is h alpha, but this product is 0, and therefore alpha satisfies fx is equal to 0. Therefore alpha is a root of fx. So in both way it is true. So now we can use this idea to check whether some number is a root of some polynomial or not, right? So let, if we take some polynomial fx is equal to 3x raised to 4 minus x cube plus x square plus 2, right? So determine whether uh, x plus 1 is a factor of fx. Is x plus 1 factor of fx? How will you check? How will you check whether x plus 1 is a factor?
X plus 1 divided. F of x divided by x plus 1.
X plus 1 is x minus minus 1. So what is alpha here? Alpha is minus 1. And if x plus 1 is a factor or x minus alpha is a factor, that means alpha must be root. So it's sufficient to check. It is sufficient to check whether alpha is a root. Alpha is equal to minus 1 is a root of fx. Correct? Because x minus alpha is a factor is equivalent to saying that alpha is a root by if and only if. So x plus 1 is a factor means minus 1 is a root or not. So let us just calculate f of minus 1. What is f of minus 1? Three plus 1 plus 1 plus 2. Is it 0?
Not.
No,
Not.
sir.
So minus 1 is not a root and therefore x minus minus 1 or x plus 1 is not a factor. That is clear, right? It is immediately we can check whether x plus 1 is a factor of this polynomial. Correct? Now there are several questions. And what are the natural questions that can be raised? If given any polynomial fx in Px, does it possesses a root? Right. Given any polynomial, is it possible that whatever polynomial is given, it has a root? Right. This could be a question. If fx belongs to Rx and degree of fx is some number n, then how many possible roots fx can have? Right. If you are given a polynomial of degree 3, degree 4, how many possible roots you can have?
N number of roots.
Means at most you can have n roots. But these are the questions, right? And in general, because if you are given 3-degree polynomial, 100-degree polynomial, 1000-degree polynomial, it is not convenient to check every time because there are infinitely many polynomials available or uncountably many polynomials available. How will you check one by one? And therefore, in general, there should be a strategy. Certainly, it is true, right? Now, what could be the natural question you can think about? Given any polynomial, does it possesses a root? Does every polynomial has a root? Right? Given a polynomial, how many roots you can have at most? What could be the questions you can raise for polynomials and roots of polynomial? How to find roots? Right? If you have quadratic polynomial, then you know formula. If you have cubic polynomial, then again there is a formula. If you have degree 4 polynomial, then again there is a method to find roots. Degree 5 polynomial, again there are methods, some methods are developed. What about degree 6? What about degree 7? What about degree 8 and so on? Right? How to find roots? Is there any method to solve the polynomials? This could be a question. What could be the questions? Is there any relation among roots of polynomial and coefficients of polynomial? Right? So these are the some basic questions, and the ancient people had these questions and they developed some theory how to find roots and does every polynomial possesses roots, and so many questions they had, and in that way the theory is developed. Right? These are the basic questions. So a polynomial of degree 1 is called as linear polynomial. Right? Do you know this? Polynomial of degree 2 of degree 2 is called as quadratic polynomial. And polynomial of degree 3 is called as cubic. Polynomial of degree 4 is called as a quartic polynomial. Polynomial of degree 4 is called as quartic polynomial. Polynomial of degree 5 is called as quintic polynomial. Then degree 6, degree 7, so names are given, but up to degree 5 some methods are developed, right? After that there is no standard method to solve the polynomials, and we'll try to see some of the cases up to degree 3 or probably degree 4. So now these polynomials where we need to solve the polynomial, what is the purpose to solve the polynomials, and these are many applications, believe me, because in any field of technology or whatever you field you select, physics, these polynomials occurs there while solving some real life problems, and you need to find roots, then only you can solve those problems. So therefore this theory of equations or roots is very essential. So now the basic question is, does every polynomial possesses a root? This is a very basic question, right? And there is a theorem, fundamental theorem of algebra. We will not see the proof, we'll just try to understand the statement. Proof is not easy at this level or extent, but we'll try to understand. So every polynomial, okay, you know what is a set C? What is C? We denote set of complex numbers. Right, set of complex numbers. And what is the set of complex numbers? X plus iy x and y are real numbers and I square is -1, and we know how to add and multiply two complex numbers. So okay, so now question I would like to ask here, does C, you know what is addition of two complex numbers, you know multiplication of two complex numbers. So with respect to that addition and multiplication, does C satisfies field axioms? Right? Does C satisfy all field axioms? What is your answer? You check this. This is again a basic question. Right? Does every complex number has an additive inverse? Does every non-zero complex number has multiplicative inverse? What is additive identity? What is multiplicative identity? And all these things you can check. And answer is yes. And then the next question I would like to ask is, does C satisfy order properties? Or does there any order? And does C satisfy, C means set of all complex number, completeness property? So these are some questions which are not very essential at this level, but you can think about. And answer of this question is no. Sir, C does not satisfy completeness property. So there is a difference actually. But from calculus or analysis point of view, these properties are there, completeness and order, all these things. From algebra point of view, we are just interested in roots. And what is a fundamental algebra? Why it is called fundamental theorem? Because this theorem has lots of applications and in algebra. So the statement of theorem is every non-constant polynomial has a root in C set of complex numbers. So every non-constant polynomial has a root in set of complex numbers. Okay. Is statement clear? What do I want to say? What is the meaning of this statement? For example, if I take polynomial f of x is equal to 2x minus 3. Where is this polynomial? This polynomial is in zx. Am I right? Is it in zx?
Yes, sir.
But what are roots? That means what is the root of, what are roots of, there it has only one root, right? 3 by 2. But root is not in z. Am I right? But root is in rationals. This root is a rational. That means if you take a polynomial with integer coefficients, roots of that polynomial might not be integers. That is the fact actually. Is it clear what I am saying? Yes. Now you look at this polynomial x square minus 2. Where is this polynomial? It is in zx as well as in qx. And what are the roots?
Root 2.
Plus minus root 2. And these are not in rationals also. And certainly not in integers. Right? So polynomial is with integer coefficients or rational coefficients, but roots are not rational. Okay, now if I take polynomial with real coefficients, is it possible that all roots are real numbers? Or it has roots in real numbers?
No, sir.
So x square plus 1. This is a polynomial with real coefficients, or you can say integer coefficients or rational, whatever. But okay, this is polynomial in Rx actually. This is polynomial in Rx. What are the roots? X square is minus 1, that means x is square root of minus 1, that means plus minus I. What is I? Root of minus 1. So this root not in R, not in real numbers, because this is imaginary number. So up to real numbers, you take polynomial with real coefficients or integer coefficients or rational roots may not be in reals, right? But in case of complex numbers, you take any polynomial with whatever coefficients, you can find roots in complex numbers, right? And therefore a complex number, set of complex numbers is the most general extension of these sets, biggest extension or complete in some sense, right? So this is what the fundamental theorem of algebra says. You take polynomial which should be non-constant. If I take polynomial f of x is equal to 5, then it has no root, right? Non-constant polynomial has a root in complex numbers. Yes, is the statement clear? Yes.